This is John Gonder for Chabot College and Las Positas College, and this is the video plan for watching this video. As usual, it's always good to watch a little bit, then pause, take some notes, and go ahead and do what it is you see me doing in the case of demonstrating things so that you can really get it down. We're talking about getting a packet on the wire. What actually is inside a packet, and what are things that need to be put together in order for it to go from your computer out onto the net? Where did those things come from, and how does your computer go about building a packet? These are really important things to know from any standpoint. If you are in computer security, ethical hacking, penetration testing, network analysis, troubleshooting, you need to know what is the process that actually happens on the computer when we build a packet. I'm intending this video to take the place of the original video Laura Chappell created about the process of getting a packet on the wire. We're going to take a close look at the individual parts of an IP packet and where they fit into the OSI model, and at what point in that process the application layer generating data, putting it together into segments that are put together at the transport layer and addressed at the network layer, and then sent out through the data link and physical layer. What are the pieces of information that are necessary in order for that packet to actually get out there and work? Where do they come from? So it's all about generating numbers at each layer, because our packet is what? It's ones and zeros that represent numbers, that represent the words that we use, like when we type in and say I want to go to a particular website and I want to get a particular file. The OSI reference model that we make use of, on one hand, delineates the process of communication between the various jobs that need to get done on your computer, from the software application generating information to the process of presenting it and maintaining a session with your opposite number on the other side of the network. And the transport layer organizing and managing the process of sending and receiving packets. The network layer, which takes care of the process of routing packets across the net. The data link layer, which takes care of the process of translating that information into the ones and zeros, and the coding for the particular physical medium that we happen to be using. At the physical layer, obviously, there has to be some hardware involved, and often there's firmware, some software that's embedded in the hardware at the data link layer. Some of the data link layer's jobs are implemented in the operating system software, on up to the actual application software, which typically is includes the presentation and session layers. But nonetheless, we have this combination of hardware and software that work together to generate the pieces of information necessary to build our packet. One important aspect of the numbers that we generate in building our packet is that they allow us to have that conversation with our opposite numbers on the other side. At the physical layer, there has to be a conversation between the physical interface on our side and the physical interface on the other side in order for the ones and zeros to get across the net. And the data link layer operates to pull all those ones and zeros off of the physical layer and hand them up to the network layer at each end. The network layers at each end take care of the job of routing the data from one side to the other and replies to the other side. And then the transport layer works with the transport layer on the other side to make sure that the data has been received and acknowledged properly. At the session and presentation layers, any conversation that needs to be set up and authenticated between the two application layers is taken care of. And then obviously at the application layer, for instance, in terms of a web browser, in a web browser application, we're in contact with and conversing with the server application at the other end. The different numbers that we will see that are used by different applications to allow us to have at my local client station a number of applications running at the same time, some of them using TCP at the transport layer, some of them using UDP, and then the Internet Protocol doing the routing of these packets that come from multiple applications and go to multiple applications on the other side, where the numbers that we assign to them, the TCP port numbers or UDP port numbers, allow the information to be sent to the correct listener at the other end. So we can multiplex. We can have multiple conversations going on at the same time, and the speaker on one end ends up talking to the correct listener on the other end. So what are some of the things we need to get done, and in what order do they happen when we're putting together a packet? Well, the analog for us in the real world for these layers is when a CEO says, I want to do lunch with the CEO of another company. Then the secretary writes that down and gives it to her assistant, and he puts it, or she puts it in an envelope with an address, and then gives that to the mail guy who decides how it's going to be shipped. And then a company that's chosen for that process manages the process of getting it across to the other side by some physical medium. They don't know what's inside the envelope. They just have that inside their own shipping envelope. But nonetheless, they manage that process of getting it across to the other side by whatever means are necessary. And then at the other end, everything gets unpacked. And based on the addressing, the numbers that are inside each layer, it's then passed up to the person to whom it was addressed. So we're going to be referencing several times in this presentation in Wireshark an HTTP download good PCAP that's in your sets of PCAPs. And if you want to look at that and follow along and use that, that would be great. And it represents the process of one side, 10.0.52.154, communicating with the other side, 204.152.184.134, and creating a TCP connection and getting a file, which is then downloaded. One thing to keep in mind in this process of getting across the net, we're not necessarily and not usually directly connected to the server on a local area network. We've got a client and there's a number of hops between us and the other side. And just like our package that we give to FedEx, they change the source and destination MAC addresses on the outside of the package. It's distribution facility 1 to distribution facility 2 or 3 or however many times it passes through these various links to get to the other side. Then the actual envelope that's inside the FedEx box is unpacked at the other end. There's a number of steps. We're going to see the MAC address, the media access control address of the actual interface of each device through which we pass, and it gets rewritten every time. Here's my MAC address, the MAC address of the first destination. That gets rewritten. This guy is now the source MAC address. Next guy is the destination MAC address. He rewrites it. He's now the source MAC address. Next guy is the destination MAC address. And so on, all the way along the net. So back at our source computer, we have layers 6 and 5 are part of the process. The application layer has generated some data. And the first thing we need to figure out is, what TCP port number will we assign locally to this process, this end of the conversation that's going to represent this particular application as different from other applications that might be running on this computer? Well, the operating system's going to choose that from the list of ephemeral ports available that are not currently assigned to other applications. In the case of our example, the PCAP file, the source port chosen was 2646 for this application. But What about destination TCP port that is going to represent the application on the other end of our conversation? When more applications may be running, we need a TCP port number that's going to point us to the one process we're interested in talking to. Well, the first thing that's going to happen is we're going to look at the services file that's present in the operating system files of our client computer. In the case of a Windows computer, it's going to typically be in the System32 drivers etc folder. There is going to be several files in there: protocol file, LM hosts file, networks file, services file, and a hosts file. We're going to look first at the services file because we want to find out what port number we should use for this particular application. Now, IANA.org assigns TCP and UDP numbers by default to common services. And so typically my hosts file is going to conform to that, although certainly the application can override what might be the normal port number list. So let me take a look inside the actual hosts file of my local Windows 7 computer. So here's that file. It's a text file, and I could actually edit it if I want to. Say, for instance, we have our own local server for web information for our company. Well, I might add a listing in there. In here, there's no listing for HTTP. There is a listing for HTTPS. But there's no listing for HTTP. I might have a server here that I want to differentiate and not have anybody connect to that doesn't actually know it's there. So I might run that on port 8080, in which case I might have an entry in that local hosts file that has HTTP as 8080. But at any rate, if it's in the hosts file or the application itself designates what it wants to be the port number, then now we have a number to assign to that destination port. If we're working with a different piece of software or a different company, often there's a particular port number already assigned to that company by IANA.org. And if you create a new piece of software, you may typically want to register it with them, so when your piece of software is being communicated with by definition on that registered port, it's not going to be confused with another piece of software or another company. Actually, it's common for certifications to want you to be able to spout back 15 or 20 of these well-known ports in the applications that are assigned to them. There are specific ranges of numbers from 0 to 65,535, which is the maximum number of numbers in the port range for TCP and UDP ports. The well-known numbers, registered ports, 0 to 1023, and then the registered port numbers for other applications, 1024 to 49151, and then the private, dynamic, or ephemeral port numbers that we are allowed to use to assign to our local process, 49152 to 65535. So either by having it assigned by the application or looking in our services file, if we were using FTP, we would translate that to port number 21. In the case of our web request, we translate that to TCP port 80 for the destination, the standard port for HTTP. Well, now we're ready to have a source and destination IP address. Well, we know what our own IP address is. It's 10.0.0.0.0 0.52.164 in this example, how do we find the IP address of the fully qualified domain name openoffice.org that we want to communicate with and get a file from? Well, we've either got to get that in our DNS cache on the local computer, or we're going to send out a domain name server request that says, hey, I want to talk to openoffice.org. What is their IP address? Let's take an example and look in a cache and see what might be there. Well, actually, first let's take a look at the hosts file. Again, remember that there is a local hosts file, and we may already have hard-coded associations between a fully qualified domain name and an IP address. This example, we can see, however, from the pound signs that those lines are all commented out. There were no locally assigned mappings. So that brings up an interesting thing, which is in security for our servers in our network farm, we can use that hosts file to prevent them from having their ARP cache poisoned by a man-in-the-middle attack by putting entries into that hosts file. Let's say, for instance, where our DNS server is, where our database is. So the server never has to actually send out DNS packets to go finding an IP address. It always knows where it can go. And that is a security aspect that we would implement as a good system administrator. So if we've already, in this current computer session, communicated with that particular website, that fully qualified domain name, and it hasn't been too long, that information should already and still be in our DNS cache. And of course, that information ages out after a certain amount of time. Now, let's give a little demo of what that looks like. So here in our Windows machine, we're starting up, and I'm going to log into it. And so this is a fresh session with our Windows machine, and we have not gone anywhere yet on the net. So let's open up a Command exe window, and I'm going to say, first of all, ipconfig, and we can start to see some information about the interfaces on this box, whether they're physical or, in the case of a virtual machine like this, that there's logical interfaces. So here's our Ethernet adapter, local area connection. Here's our IP version 6 address. And we got an IP address 192.168.0.10, an IP version 4 address, a subnet mask, and a default gateway to the router which can access the outside world. It allows us to send packets to locations outside our local area network. And we're going to talk about default gateways in a minute. So I can see more information by saying ipconfig/all, and in that case I see more information about these individual interfaces, both logical and physical. I can see the lease time for this IP address, when I acquired it and when it expires, and some other information. Now I could also the ipconfig with a question mark, and I can see all the information about this particular command, ipconfig. Let's do the question mark. There we go. So one of these subcommands is to display the DNS cache, and one of them is to flush the DNS cache. So I'm going to go ahead and display the current DNS listings. ipconfig/display DNS. And I see nothing in there. Oh, I don't already know any mappings between a domain name and an IP address. I have not acquired any, and they were not already manually entered here. So if we wanted to go to openoffice.org, then I would need to send out a DNS request packet, and I would get that IP address from the domain name server. Now let's open up the browser and go to a few places quick. Now, if I was capturing all this traffic with Wireshark, I could see a lot of domain name server requests going out here. Let's go to Chabot, but that's really enough because CNN has so many ads. We're going to see a lot of requests there. Now, previously, there was nothing in the cache, right? So let's give that command again. And wow, baby, there's records here in the DNS cache for BW11. That's the banner system for CLP-CCD, Chabot and Las Positas. Now, you saw I didn't actually even go there, but the process of going to the Chabot main web page, that page included a piece of information that came from that other server. So for each element contained in the web page that was located somewhere else, there was a DNS request and reply so that the browser could bring that information in. Same thing, we're going to see a long list of names and IP addresses for the elements included in just those two web pages we went to. Look at that stat counter. Some kind of stuff that keeps track of you on the net. They're watching you. So now, if I wanted to go to one of these places while we're building those packets, that information would already be in my DNS cache. And the next time I go there, if it's not been too long, that information will still be there, and I'll no longer be sending out DNS requests for it. So the process is we want to go to Chabot, so we do have that information already in cache. And then as we get the web page, it wants to show us more information. So do we already have the IP addresses of those places? Yes, we do. And so it's faster, and we no longer have to send out a DNS request. We can go ahead and build those packets. So either from DNS cache or by sending out a DNS request, we're going to find out the IP address of that fully qualified domain name that we want to contact. Then the next thing we're going to need to know is, how do we get out of here? Is our destination not on my local area network? Do we have a route to that place? We're going to need to be able to find the media access control address, the MAC address, of the first hop on our way there. So I know my own MAC address, the address burned into the interface that I want to send my packet out of. The first place I would look for that destination MAC address would be the MAC address of my gateway router, if this is, as I know, not on my local area network. So again, if I have this, in this case in the ARP cache, if in the recent past I've sent out packets to the internet, then I'll already have that relationship between the IP address of my gateway router and its media access control address there in the ARP cache. So if I can just fill in that destination MAC address information in my packet, I will. Otherwise, I'll have to send out an ARP packet, Address Resolution Protocol packet, to get it. So I determine if it's a local address or not by comparing my IP address to the destination address I want to get to. So if we're on the same local area subnet, then I can just look in my ARP cache to see if I have a MAC address for that destination IP address. And if not, then I'll ARP locally for the MAC address of that IP. So I can look and get that address with an ARP if it's a local destination. Now over here in Wireshark, our example trace file, there's just a conversation between the local device and the server. So if there was an ARP necessary, it was not captured in this file. If we do need to ARP for that information, we'll use the destination IP address in our ARP. If our router knows how to get there, then it will just reply itself and say, no worries. You just give that to me. Here's my MAC address, my IP address. Don't worry about that. I will take care of it. So now we're looking pretty good. We've got something that kind of looks like this. We've got a request that goes out from the source IP address to a local, and a local ephemeral TC port number assigned to our conversation, to the destination IP address and port number assigned to the service we're looking for. And when the package comes back, it's going to be reversed, and it's going to have as the source that server's IP address and its TC port, and the destination will be our IP address and our local port number for that conversation. So that information will end up being passed to the correct process on our local computer. So now we can see there's a lot of places where things can go wrong, and that's where our understanding of this process and these steps will help us find problems. For instance, we could be trying to go to an FTP server that's operating on a non-standard port. We're sending to an IP address and we're trying to talk to somebody on port 21, but there ain't nobody there. We could be looking for an IP address that's not in our cache, not in our hosts file, and we don't get a good or a timely response from the DNS request. Maybe DNS is down. And if our destination is local and the MAC address is not in our cache and we can't get a response to our ARP, then that's our problem. So in each case, when we're looking for something, we're going to transmit a packet. Maybe we compare these two IP addresses. Our destination is not local, so we need some routing information. So maybe we can find out in a hosts file the network on the network gateway, and so we're going to try to get a MAC address if somebody has a gateway, a router, or anybody to get us off this net. Maybe the router is not operating properly or does not know a currently available route to that destination. Sometimes routes go down. So in each of these cases, things can go wrong. We may not be able to get the information. Also, the information may be poisoned or incorrect. That's why I mentioned the importance of using a host file to secure servers and, in general, being aware of the security of our network, so we're not going to be prone to a problem like ARP cache poisoning. So once we have a fully formed packet that has each of these parts, then we can have a conversation on the internet. And all the various locations that are running locally can multiplex their conversations properly to all of their destinations out on the internet by means of the port numbers and IP numbers that we found in the process of building our packets. So back in Wireshark, when we look at the conversation in this trace file, we see the result of each of these packets that have been built. The SYN, the SYNAC, and the ACT packet, the first three packets here, the three-way handshake that creates the TCP connection. We have a synchronization request from our local telnet saying, I'm here and I'd like to talk to you on port 80 if you've got somebody there. And then we see a SYNAC back to our port 2646. That's going to say, yes, I do have somebody listening on port 80, and we can go ahead and build a pipe with which to send some data. And then there's an acknowledgement back that says, cool, yep, now we're connected. My local telnet, port 2646 to your 204 net, port 80, and our two applications can start to work together. Then at packet 4, we start to see that GET request from the browser to the server for a file. And if we look here and there, that our destination MAC address, what is it going to be? It's going to be the MAC address of our router to get off our net, the first hop. The source MAC is going to be my local area networking interface on my client. Then at the IP layer, my source address 10.0.52.164 and the destination address 204.152.184.134. And when our packet is built with the source port 2646 and the destination port 8080. And so on all the way down. The process of building packets goes on in the background, and we don't really think about that. But understanding that process is really important for us to have in the back of our mind all the things that need to have happened correctly for each and every packet that goes in and out of our computer. Now, I want to point to another resource, and that is this Wikiversity. When I put this in, we're going to see this come up. And here's a good explanation of and activities for viewing the hosts file, viewing the DNS cache, and understanding the operation, and a lot of good stuff for you to practice. If you want to take a look at the host and services file in your own computer, make sure to take a copy of that file, put it up on the desktop, and look at that so that you don't accidentally make a change that will prevent your computer from working properly. Backups are always good, really good. Always working on a backup instead of the original important critical system file. That's very important. So now you see the processes that your computer uses, application working with the operating system, the software, firmware, and hardware built into it to build every single packet that goes out of your device and disassemble and make use of the information inside every packet that comes back. So I hope this gives you a good understanding of the processes that are going on, so you can think about that and remember that when you're trying to diagnose a problem or when you're thinking about working on security for your systems.